This is almost a computer. We have a full-fledged central processing unit over here on the left. We have 7 bits of external input coming from the user up here on the top. We have 8 bits of internal working random access memory right along there. And just below that, we have 8 bits of external output back to the user. So we have pretty much everything we need to call this a computer. We have a CPU, we have RAM, and we have I/O. But those 3 building blocks in and of themselves are kind of inert and useless unless we have something to tell them what to do. The final piece that we're missing is read-only memory, some kind of ROM to give this concoction of insanity instructions to actually do something. So that's what we're going to get to work on today. We're certainly not going to finish it, but we're going to take that first step towards building a paper tape reader. So paper tape is going to be our stored programs. The reader will read them in, and the processor will execute them as they come in. Now, normally when I do my little intro, I often do a camera cut after that to a different angle so we can start talking about what it is we're going to start working on that day. But I'm still standing in the same spot. The camera still hasn't moved an inch because there's still just so much more that I want to talk about and bring you up to speed with on this project for multiple reasons. It's been like 6 months since the last update on this project, so there could very well be a large number of people that are watching this episode and have no idea what this is. But before we get into any of this, there's 2 things I gotta say. The first is just a bit of a heads up. This episode is going to be a lot of hand waving and a lot of me talking at the camera, and we're not actually going to build all that much. We're going to do a little bit of breadboarding a little later in the episode, but we're not going to construct the finalized paper tape in this one. I'm just trying to bring everybody up to speed on where our designs are right now. And if you're one of those people that tunes in just to watch me really hunker down and get to work and build something, this might be an episode that you would want to skip because it might be a little boring for you, but I do think that the context of what's going on is quite important here. And the second thing I want to say is I do realize the irony of scrolling a bunch of Patreon names right across the very thing that I'm trying to talk about. But these people are absolute legends. Without them, I would not be able to put food on the table, much less do this hobby. So without their amazing support, none of this would be happening, particularly that person. That person is an absolute legend. But I want everybody to hop into the comments and give all of these guys just a massive thank you because I can't thank them enough. They have, you guys mean everything. Thank you so much. But now that the names have scrolled off the screen, what on earth is this project? And if you know, you know, but if you don't, this is almost impossible to decipher by looking at it. And yeah, it is pretty much laid out exactly like it was when in the intro that I pointed out. We do have a central processing unit here on the left, but it is based on the Motorola MC14500 1-bit industrial control unit. This is a little 1-bit microprocessor that Motorola built in the 70s to act as a replacement for relay ladder logic in industrial applications. Now I took that design and I modified it slightly. I eliminated their logic unit and replaced it with a proper arithmetic logic unit so we can do addition and subtraction on this now. But it is important to note that while it is a 1-bit processor, it is not a bit slice processor. We can't stack multiples of these up to get wider bit widths. This is full-on 1-bit data bus, 1-bit in and out. And that tends to cause some confusion when I tell everybody that this is a 1-bit computer, and they realize that it has a 4-bit instruction. So we have 4 bits coming in to tell it what to do, and we have another 4 bits that we're using for addressing. So it's a 4-bit computer? Well, no. We say that a computer is however many bits based on the size of the data bus. The 6502, for example, has an 8-bit data bus, but it has a 16-bit address bus. We don't call it a 16-bit computer though, we call it an 8-bit computer. This has a 1-bit data bus and a 4-bit address bus. So it is a proper, full-fledged 1-bit computer built out of vacuum tubes. Now, what's going on over here on the right is input, output, and working memory. Input is literally just 7 bits here, which is a little strange because everything else with our 4-bit addressing, we should be able to address 8 bits, right? Well, 1 bit is a loop around from an internal register in here, so we can access that register again through just a simple instruction. So that only leaves 7 bits available for the user, but that should be plenty for getting simple input and output from the user. Now, speaking of that output, these 8 bits down here are built exactly the same as RAM, but we can't actually read anything from them. They're technically write-only memory. It's capable of being read, but not capable by this system. It's capable of being read by something external to the system. And the outputs on all of those are available on this header down here. So we could theoretically plug something into here that goes to an external system and use this 8-bit register to control whatever that external system is. It could be memory expansions, it could be traffic light controllers, or anything like that. And finally, we have 8 bits of working RAM right here in the middle. This is proper read-write RAM, so we can load it up with stuff and take it away and do all the things that you would normally do with RAM. But this giant gaping hole in the center here is for our read-only memory. And that's where I want to build a paper tape reader. There's a couple of things missing from this computer. It doesn't have a clock, and it doesn't have a program counter. Now, a program counter normally counts up in binary, and each step on the way up is the instruction that we're currently executing. Now, the program counter offers some benefits and allows you to jump forward or jump backwards, but that is incredibly intensive on the number of tubes or transistors, particularly for the binary counter themselves, as well as the decoder to decode the binary value that's coming out of that counter into individual signals that can then execute specific instructions. So I've opted to just eliminate all of that in the quest for simplicity and just have the paper tape itself be the program counter. Because of the way that this machine is designed, we have a 4-bit instruction, we have 1 bit for selecting input and output, and we have a 3-bit memory address. And since that's only 8 bits, we can fit an entire instruction with memory address onto a single byte, which just so happens to fit perfectly within the width of a paper tape. So 8 level has 8 bits on it. That's our perfect instruction right there. And I got tired of standing up, so we're sitting down now, which is actually probably a good idea so I can have my notes in front of me so I actually know what to talk about without rambling on too much. But we are indeed going to use paper tape. But when I say paper tape, what do I mean by that? Well, I happen to have one here on the desk. This one says format tape or heading program. And it's a pretty short program. You see maybe only 10 bytes long. And you can see there's a long header and trailer, so we can kind of ignore that. The bulk of the program is right here in the center. And you can see there's actually space for 9 holes on this tape. There is an offset center track that has smaller holes. This is actually for tractor feed or clocking. So in a tractor feed system, there's like a little cogwheel that pushes through those holes, and that's what pulls the tape along. In optical systems, you can actually shine a little light through there, detect that light, and use that to clock the system. Hint, hint, wink, wink. But you can also see that outside of that center feed tractor area, there's space for 8 more holes, and that's our 8 bits that we're going to use to create our instruction word. Although this one's going to be using them potentially slightly differently than that. As you can see, they only actually use 7 total. So that 8th one is over here on the left, and you can actually punch that with any kind of commercial paper tape punching machine. So that's how we're going to build our tape. But how are we going to read it? And well, there's a couple of problems here. The first is that, well, when I look at this, I can clearly see the bytes, but if I need to build something mechanical that can actually read these bytes at the precise timing that we need it to be, it's quite difficult because the tape is actually very, very small. I have this page here that Figulus found for me out of one of the IBM manuals. Thank you so much for that. But it has a diagram on the bottom here that shows all of the measurements of paper tape. And you can see that the diameter of the holes is just 0.072 inches. And the smaller tractor feed holes are 0.046 inches in diameter. And the holes are only 0.1 inches apart from each other, but that's measured center to center. So the actual amount of remaining tape that is separating the holes is tiny. So how are we going to be able to read exactly which holes are open and which holes are not, indicating which bits are set and not? And well, this is what I've spent the last 6 months trying to suss out. Turns out building a paper tape reader from scratch isn't exactly easy because, well, there's a lot of options, but they're all difficult. Initially, I was thinking of going for something very, very mechanical, and I found this DIY paper tape reader that somebody built online. I'll put a link to it in the description below, but I really love this design. They just took a bunch of paper clips and they have a nice round curve to them, and they have those pushing against a piece of single-sided PCB, and that single-sided PCB essentially creates a power plane or a ground plane, depending on how they're wiring it up here. And as the paper tape passes underneath those paper clips, it either makes or breaks the connection between the paper clip and the plane below it. And so you can detect it that way. And of course, he built it out of, looks like hot glue and little blocks of wood. And I would have machined it out of something a little more robust that would have centered the tape and gotten the specifications down to the level of precision that we needed to get this done. But I started thinking about it, and the more I played with this tape, the more it became apparent to me that this may not be the best idea, because you can see already that this tape is getting pretty weak just from bending. And this goes back to what I was saying about the amount of paper that is in between two holes is very small. And I want this machine to be able to go to GCF Southwest and be on display for 3 days straight, running a single paper tape loop all day. And I think the wear and tear of a paper tape loop running underneath this kind of mechanical follower type of reader would eventually just tear the tape to shreds. I don't know how many loops we'd be able to get out of it. So we need to maybe not go so mechanical and take a book out of everybody else's page here and go optical. Now that creates a bit of a problem because I want to be period correct here. I am using a whole lot of vacuum tubes, and I do use some diodes, but germanium diodes were in widespread use on vacuum tube computers throughout the 50s. So I just need some kind of way to detect whether light is passing through a hole or is being blocked by a hole. And well, I need to get a photodetector tube, and I have some of those, but not here. Let's go grab those. To quote Bane, time to go mobile. We're walking inside. That's where the photodetector tubes are. Hey, puppy. All right, requisite pets done. Let's see here, not in that drawer. There we go. Display and photo tubes. That's what we were looking for. All right, we got a lot of cool stuff in here. So let's crack this open and see what we got here. We've got something in a Westinghouse box there. This is not photo related. It can go off screen. There we go. That's a photodetector tube. That's a pretty cool VFD. More stuff inside of boxes there. There's another photodetector tube. It's a relay. Yeah, this continues. It's just awesome VFD after random relay tubes, after more different types of photodetector tubes. Yeah, all sorts of really awesome stuff in here. Well, I don't have that many of them. I've got 3 of these tall boys and then 2 of these kind of shorter round boys here, but they're both essentially kind of the same idea. And these tall boys actually do work at low voltages. I've actually tested these at plus 24 volts, which is incredibly important because the entire vacuum tube computer is purely low voltage. There is nothing greater than plus 24 volts or minus 12 volts at any point on that computer. We are not bumping up to a high voltage to run the B+ on the tubes. Nope, we are running those 6AU6s at a B+ plate voltage of 24 volts only. That's pretty wild, but it also adds an extra level of constraint to whatever design we're having to make. But like I said, these tubes actually do work at 24 volts, but there's a big problem here, and that is that it's huge. If we compare it to the size of our paper tape here, how on earth would anybody ever go about discerning the light that is flying through the individual holes with a detector that is this large? And the answer is I'm not even gonna try to attempt that, but somebody has attempted it in the past successfully. And that was on the Colossus computer. I have a couple of interesting photos here that is from an article that somebody sent me, and it's a really fascinating way of getting this done. They have a lamp and then they have a condenser, and as I understand it, this condenses the light down to the same width as the paper tape, but the light then passes through or does not pass through the holes, and then it hits a lens that then spreads that light back out, and it flies all the way across the room and it hits big giant detector vacuum tubes like this. It's absolutely insanity. I mean, I have no idea how to make this work. I mean, these diagrams are the first I'd ever seen of it, and they got it to work in the 40s, but I have zero confidence that I would be able to make something like that work in here. And it wouldn't fit in my space constraints on that backing board anyways. It would be massive. So we got to come up with something else. And well, somebody had an interesting idea by using I think it's called a Nipkow disk. I'm not really sure. I have a picture of it right here. Essentially, you have a single photocell, so we just need one of these. And then you have a spinning disk that aligns up with each of the 8 individual dots. And then you essentially feed those dots serially into a shift register, and then you hit that shift register all at once. The good news of this is that we only need a single photocell, but we do need to build a shift register, which is not easy. That's pretty tube intensive, and you have to build a very, very precise condenser lens and an aperture mask that masks out the light flying through the holes. Mechanically, this is quite complex, and I don't think that's the way I want to go either, although I do think that's a really cool way to do it. Ultimately, we're going to do it optically like Bendix did it. On my vacuum tube computer, I'm aiming for about period correct to 1955. Now, I am using modern Schottky diodes, but every one of those Schottky diodes could be replaced with a germanium diode, and it would work exactly the same. So the design is actually period correct. It's just that finding hundreds and thousands of germanium diodes these days is quite difficult, so I'm just using modern diodes. But I didn't want to use modern phototransistors, so I need to use something that's period correct. And the Bendix G15 actually used period correct photodiodes. This seems wild to me. I had no clue that photodiodes were available in 1956, but I got a Bendix right over there with them bolted straight to it. So there we go, proof positive that using photodiodes for a for optical paper tape reader is 100% period correct. Now the question is, which photodiodes am I going to use? Now, you can find 5mm photodiodes pretty easily, but those are huge comparatively to the size of the holes that we have here. And I initially had this idea of building out these kind of light directing tubes that were the correct size, that would spear off to the sides and direct the light to the larger photodiodes. And I ran down this path of design quite extensively. I even ordered up a bunch of parts and started thinking about how to properly machine an aluminum block to have this kind of interesting pattern going on where we could get all the things fitting correctly. And, you know, I just needed to find the right kind of photodiodes. You see, Bendix was able to keep the mechanical aspect of the optical reader so compact and simple because they found some really unique photodiodes. Instead of mucking about with light pipes or complex physical designs, they instead just found little photodiodes that are 0.1 inch in diameter. That makes it super easy. You just machine a block with the correct hole spacing, and then you bolt your little diodes in. And these are incredibly hard to find these days, but after a bit of hunting, I did find some. And these are them. And you can see they're absolutely tiny, but I've got one pulled out here. We'll lay it right next to the photocell next to it, and you can see the size difference is staggering. But these, I think, are going to be perfect because these are 0.1 inch in diameter. They're the absolute perfect size, and I have 10 of them in this bag, so if one of them is bad, we do have a spare because ultimately we're going to need 9 of these, but that's still cutting it a little tight. I'm hoping to order some more from the same seller as soon as he becomes available. So we've got the thing that makes time travel possible.
Great Scott! I know, this is heavy.
I mean, we've got the thing that makes the physical construction of our phototape reader much easier, and machining out the block to hold those is going to be a walk in the park compared to some of the other designs that we were thinking of. And that's actually what we're going to get into in the very next episode. But before I can finalize the three-dimensional design of this reader, I need to figure out what we got to handle electrically first. So we can set up a simple inverter with just a photodiode and a 100,000 ohm resistor that goes to 24 volts. Now these particular photodiodes are 3F42s, and they, I think, have a reverse voltage of 30 volts, so we have a little bit of headroom there with our 24 volt going in. So we shouldn't be pushing the photodiode outside of its design constraints with this 100,000 ohm pull-up resistor to 24 volts here. And then we take the output off of the junction between the 100K and the photodiode, and we run it into, well, my standard 6AU6 inverter. To give this a little test, it only felt appropriate that I get out my vacuum tube voltmeter for this. This is my Conar National Radio Institute Model 211. It is a proper vacuum tube voltmeter. It was surprisingly affordable, and it's pretty fantastic. Also, I just love seeing a big analog needle sweep across the screen here. Now, the breadboard is set up moderately simply. We have 2 light bulbs here. These are both 6 volt pinball bulbs because we have a lot of these floating around, and I'm actually running them in series off of 12 volts DC. So they should give out a decent amount of light without being blindingly bright. Also, we have 2 vacuum tubes set up over here. The second vacuum tube is just an overglorified ballast resistor. The vacuum tubes are 6AU6s. That means they have a 6 volt filament, but my bench supply here doesn't supply 6 volts, so we're running the filaments off of 12 volts, and I'm just putting 2 of them in series. That second vacuum tube is doing nothing else. So we have our lights going into our very tiny photodiode here. The output of that goes into the input of this vacuum tube, and then we're checking the voltage off of the plate of this vacuum tube, and right now you can see that it's sitting at, looks like just about 2 volts, but the lights are off. So let's go ahead and flip the switch to turn our little lights on here. And yeah, you can see the needle went screaming up to about 24.5 volts. That's our supply voltage coming out of there, and that's excellent. But the big question is can a little paper tape like this actually block the light? Because these paper tapes are somewhat translucent, but oh, you saw it right there. If I drop this down, check that out. The paper tape blocks just enough light for our logic high to drop all the way back down to about 2 volts, almost 2.5, but that's a great logic low, and then right up to 24 volts. That is gonna work absolutely flawlessly, I think. That is really, really cool to see in person. Boy, that's a lot of fun. Look at it go, look at it go. there you have it. Pretty much like I said, just a big ol' exposition dump today. Just a lot of hand waving and talking at the camera, but at the end of it, we have a fully functioning proof of concept for our paper tape reader, which means we can now move forward with building the actual thing. And once that paper tape reader is built, now there's nothing left. It's complete. It's a working computer, which is just the craziest thing to hear come out of my mouth, because when I started this many moons ago, I never thought it would get this far. I am absolutely ecstatic to see it start to come to fruition and to hopefully see it executing code before too long. Ultimately, maybe not really soon, I do want to build a traffic light demonstration that we can plug into the output of this thing and then have a traffic light controller program loaded up on paper tape. So when we go to an event, we can just load up the traffic light paper tape, and there we go. We have a real deal traffic light demonstration going on. That would be, I think, a really cool demonstration of this thing. But first and foremost, we need to machine the block that is going to hold all of our photodiodes. So I need to sit down and get familiar with a 3D modeling program. So if you have any recommendations about what 3D modeling program to use, I've never had to do that before. So if you've got some recommendations, let me know in the comments below. But in the meantime, I want to thank you all so much for watching, and I hope to see you in the next one.